So and then I'll talk about how to possibly get the muon G-2 only from muonium spectroscopy and some 3D. This is the hydrogen session, but we'll think about of muonium as an isotope of hydrogen, so it will be okay. So you can say that one of the we have more than one G-2 puzzle. We have the experiment, which the experiments agree, measuring the muon G-2. Both are dominated by statistics, and it's a similar experiment, but still they have slightly different systematics, which are smaller than the statistical uncertainty. And they disagree by 4 standard deviations with what may be considered as the agreement on the theory of the G-2, but of course we have a more ab initio theory done with lattice QCD, which doesn't agree with the other theory. So depends who you ask, these are the good, the bad, and the ugly. And depends who you talk to, you can assign each one its character. So the main question is, what is the reason for the 4 sigma discrepancy between experiment and theory, but also, and that could come from beyond Sarat model physics. There are many models that try to interpret it like that. And another question is, where does the difference between the two theories come from? And there's also a new physics explanation for this difference, because the lattice QCD calculation is done only with a computer, but the so-called white paper calculation is calibrated by experiments, which may also be affected by new physics. Putting the muon G-2 puzzle in a slightly broader context, it's one of the several hints for what we call charged lepton flavor universality violation, along with the Cabibbo angle anomaly and more intensity or high energy frontier observables, which do not agree, usually on the level to 3 to 5 standard deviations, or even up to 7 standard deviations, depends a bit on the interpretation you give to the discrepancies. So we're starting to smell maybe a harbinger of new physics, but of course we would like to be sure. And there are many theories which connect these small anomalies to, for example, leptoquarks kind of connect most of these new anomalies, certain scenarios of leptoquarks. And you can read about it here, but the main point is that we are very interested in figuring out if it's real or not. So clearly, if we can determine the muon G-2 or a mu I'll use in this presentation, so G-2 over 2, in a very different way than by putting a muon in a storage ring and looking what the magnetic field does to it, would be very interesting. And we want to do an experiment with very different systematics. And as you will see, of course, this is very strong motivation to do. It's also very hard. It's going to be a very difficult combination of experiments and theory. And that new way of finding the G-2 will use a hydrogen isotope called muonium. To iterate very fast, muonium along with positronium is the simplest two-body system. We already got this feeling in the previous lecture a little bit, that when you don't have finite side effects, theory is kind of straightforward. So it's almost, you will see what's not straightforward today, but it's definitely more straightforward than systems with a nucleus. And also gives access to laser spectroscopy access to a 2nd generation particle, but the muon lifetime is 2 microseconds, which means that unless you work very hard, but the order of magnitude of the line width which you can get in muonium spectroscopy is about 100 kilohertz. So that's not bad, but it limits mostly the methods in which you can use to do spectroscopy and not necessarily your precision. You cannot trap muons and cool them down and do your experiments. So that really limits the lifetime, limits the methods quite a lot. Also, you need accelerators to produce muons. And for example, in our lamp shift experiment lately, we used 10 in the 10 less statistics than what was used in the original lamp shift measurement in hydrogen. So we're really limited in statistics when working with muons, but this is always getting better. And muons are born at high energy. If you want them at low energy, you have to sacrifice several orders of magnitude of statistics. All right, so the energy levels of muonium are very similar to hydrogen. In the gross structure, the only difference would be the reduced mass correction. So you can probe it via 2-photon you can do the 1s2s with a similar 2-photon spectroscopy, the lamp shift for the fine structure with microspectroscopy on the gigahertz level. The difference to the growth structure would be on the order of the reduced mass corrections, which is the mass of the proton over the mass of the muon. And then if you want to look at high order recoil corrections in QED, then you have to go to the power of n in that. So high order recoil corrections would be completely different between muonium and hydrogen. Muonium will have a much larger hyperfine structure. This helps a little bit with the experiments because it separates out the peaks in the lamp shift or in the 1s2s, and also increases the relative uncertainty in which you can get the ground state hyperfine structure. So it's 4 gigahertz and not 1. Of course, there are no known finite size effects, and hadronic effects are usually much smaller. Up until recently, this was the situation and the state of the art in Muonium spectroscopy. So the 1s2s measurements have been done in RAL in the UK, the RAL accelerator. And 1s2s is a few petahertz, 2.5, and they were measured with 10 megahertz accuracy. The 1s hyperfine structure was measured at the LAMP accelerator. So hyperfine is 4 gigahertz. It was measured with 50 hertz accuracy. And the best lamp shift came from Triumph. It's about 1 gigahertz, and the uncertainty was about 12 or 13 megahertz. We'll hear 2 days from now the museum collaboration working at the JPark accelerator. They want to improve the hyperfine structure by factor 5 to 10, so by an order of magnitude. And we will also hear, and we also have a poster from the Mumas collaboration, which we will improve the 1s2s transition in muonium by 3 orders of magnitude. So this would be a major improvement going from 10 megahertz to 10 kilohertz. And the Mumas collaboration also measured the lamp shift in muonium, and we improved it by an order of magnitude. But still, you can imagine with current techniques and accelerators going to a few tens of kilohertz. That's the order of magnitude where we think this can be improved with the current statistics. An important note for this talk, and I'll go into it more, is that where QED uncertainty lies. And as you can see, QED, uncalculated QED terms do not contribute so much except for improving the 1s hyperfine transition. It's already limited by QED, or if you want to get the mass of the muon from the ground state hyperfine transition measured, you're limited not by the measurement uncertainty, but by uncalculated terms in QED. So we'll go into that more. Then if you want to start combining measurements in muonium, the lamp shift is not very sensitive to fundamental constants, so we'll focus on 1s2s and the hyperfine. So 1s2s is, of course, the reduced Rydberg constant times the small corrections. It means that from the growth structure of muonium, you can get the Rydberg constant with the same accuracy as your measurement. Or if you take the Rydberg constant from hydrogen, so that's about 2 parts per trillion, and depends where you want to take it from CODATA, or use the proton radius from ionic hydrogen. So 1 to 2 parts per trillion for the Rydberg constant. Given Rydberg constant, you can check what is the charge of the muon compared with the charge of the electron. From the CPT theorem, or even from causality, they should be the same in an EFT, and you can get the muon mass. Of course, this is a correction, so the mu mass goal is to measure with about 10 kilohertz or 4 ppt, and this would translate to the Rydberg constant or the muon charge with 4 ppt accuracy, and this would translate to 1 parts per billion accuracy on the muon mass. Now, if we're going to the ground state hyperfine structure, here we're proportional to the magnetic moment, the mass, the units, so the Rydberg constant, alpha, and corrections. So if we take Rydberg from hydrogen, the muon magnetic moment from FNAL's measurement, alpha from recent measurements, we can get the muon mass from the ground state hyperfine structure. And assuming, forgetting about QED for a second and using the museum goal, we can also get the muon mass from an improved measurement of the hyperfine structure with 1 or 2 parts per billion accuracy. Depends where QED, how much the QED uncertainty will improve. So when you have 2 numbers which you can get from different methods, you can combine them to get something else. In this case, it's most interesting that combining the goals of the museum and Muos collaborations, we can get the anomalous magnetic of the muon with about 3 points per million accuracy. Would that be interesting? Of course, I'll get into the QED corrections in a sec. So how interesting that would be? 3 ppm in the ongoing measurements in theory would put the uncertainty in the G minus 2 as determined by spectroscopy somewhere around here. So interesting enough, so it's on the order of the discrepancy, but still when looking at that, we really want to improve it more. And here I will explain what is needed for that. It's quite a lot, but it's still, I think, less than building a storage ring. And so less than $100 million in 20 years. And maybe an order of magnitude less. So to reiterate, the current efforts will be dominated mostly by the experimental uncertainty in the hyperfine structure and the theoretical uncertainty in the QED of the hyperfine structure in Muon. So what are the quite demanding improvements that needs to be done in order to take the G minus 2 from Muonium, which is ongoing now, this work, to say around 1 ppm, where it would start being competitive, maybe not with the best experiments, but with the discrepancy and with the uncertainty in the theory. It would be an interesting input. And so when looking at the future or the edges of something, it's usually best to look where are we going to really hit the wall. And I believe, but you can correct me, that the wall is hadronic uncertainty. That's the part which is dominating the theory and the Muon G minus 2, and that is the hardest part to improve. So the hadronic uncertainty in the 1s hyperfine structure, as much as I could gather, would contribute about 0.3 parts per million to the uncertainty of the Muon G minus 2 as determined from Muonium spectroscopy. So this is quite far away from our goal. We are not expected to hit this wall anytime soon. If we did, then we're already as interesting, very interesting for the G minus 2 puzzle. Next is experiments and QED corrections. So I'll start with identifying the main contributions to QED that are needed to be improved in order to improve features.
But it is the same hadronic uncertainty which contributes to the G minus 2 of the Muon.
Yes, they are correlated.
They're correlated very much. So it means you can
completely have completely different systematic uncertainties in the experiment.
Yeah, but if it is correlated, means you can gain again on this. Because so you can, if it's the same, you can account for this. And with the comparison, you can compare your result with G minus 2, assuming the same vacuum for the same hadronic contribution.
I see. So it depends if you take the hadronic contribution from the lattice calculations or from the white paper.
But what I want to say that you can take the same vacuum polarization in G minus 2 and in your hyperfine splitting.
I see. So it will not limit this interpretation. Exactly. I understand. So let's identify the QED conversions, because currently hadronic contributions are even less important than I thought. Okay, this is a bit dangerous to put in such a conference, but I'll do my best. So recently, Gianluca collected all of what we consider to be the important input to the lamp shift in Muonium, not in hydrogen, but here we compare with hydrogen because this is the session especially. So most of the non-recoil contributions are, of course, the same up to very small corrections. And then you have a lot of recoil contributions, which depends on powers of the mass. And we didn't put an uncertainty in hydrogen because it's smaller than the last digit recently. And maybe it's important to say we took the references in code 18, but we augmented them with the latest paper by Pahuski, Savelli. ADAS put a new paper with higher order recoil corrections, and we had to use a paper from 2002, which is the only one which accounted for, where is that? Here is this guy. For this second order recoil corrections. These are completely negligible in hydrogen, but they are not negligible in Muonium. So it's about a kilohertz in the Muonium lamp shift, and because it's only half of the correction, we put another kilohertz of uncertainty there. So the two main contributions to the uncertainty in the lamp shift in Muonium, which would be the uncertainty also in the 1s lamp shift in Muonium, are the calculation of the corrections of second order in mass non-radiative from 2002, and the radiative recoil, which you all know because it's the main contribution to many other observables. Saying that again, so the radiative recoil to the first order in mass is currently dominating the Rydberg constant if you take the muon mass directly from ionic hydrogen, and if you take Savelli's update to the 2 and 3 photon uncertainty. So, okay, there's a very strong motivation to calculate. It also dominates from Poetsky's paper the usability of the hydrogen deuterium lamp shift if you take the radii from ionic hydrogen and ionic deuterium. So new physics searches with the hydrogen deuterium lamp shift, for example, are currently limited by this same radiative recoil correction. So there's a strong motivation to improve that. The second order in mass recoil correction was, yes, calculated in 2002. It has a completely negligible effect on hydrogen, not so negligible on the hydrogen deuterium lamp shift because it doesn't cancel because it's second order in mass. And I don't think it was ever taken into account. So I hope it also gives motivation to calculate. And in the paper, it says that they calculated this is the hard contribution, that the soft contribution is missing, and it seems straightforward to calculate it. So maybe it's not such a bad idea. I, of course, have no input on that. If we take these corrections at the uncertainty on the Q, that is not hard. Can I ask you to calculate it? Because I asked Sonetsky. Okay, so that would be also important for the hydrogen deuterium lamp shift, and I don't think taken into account. Okay. So the uncertainty in the 1s2s currently is about 7 kilohertz. Maybe after calculating that one, which is easy, it would be about 5 kilohertz coming from QED. For using the 1s2s to get the muon mass, use that as an input to the hyperfine structure and use that to get the muon G-2, we don't need a lot of improvements to QED, maybe a factor of 2 on 7 kilohertz. So a small improvement in the QED of lamp shift is needed in order to do that. Of course, as you guessed, the hyperfine structure is in much worse shape. Today, the most precise muon mass, you can get it from the hyperfine structure with a very large input from QED, which I think, where is Savelli? He thinks it's also underestimated, so it's even larger than uncertainty in QED. So there's a strong motivation to improve the uncertainty in QED of the hyperfine structure in muonium, and someone improves it today, we'll get a better muon mass today. And of course, these are the contributions. And to get a competitive value of A mu, we need to improve the QED uncertainty by an order of magnitude. Now, I contacted ADAS. He's working on it. I think he's the only one working on it, as far as I could see from the literature, at least. So I think that would take some time. The experiment will be quite hard as well. So I hope this can be done at the same time. And there is some. This is not a paper about the hyperfine, but they say I essentially you to that they're working on it, basically. So they think they can improve it by order of magnitude, but I don't know if it will take 5 or 10 years. But it's definitely needed. It's currently needed because we'll see in the museum lecture that they are quite close to improving the ground state hyperfine, but without an improved 3D correction, we will not be able to do so much with an improved experiment. Next are these two experiments, the 1s2s and the 1s hyperfine, and these are dominated mostly by statistics or statistics-related systematics, because we don't have a lot of muons. For getting a better A mu, a modest factor 2 or 3 of improvement upon the mu mass goal, which is 10 kilohertz, is needed in order to be really competitive for A mu. Because most systematics when using a CW laser cancel, but you have low statistics, and for 2 or 3 factor improvement, we did factor 4 or 10 more statistics. For the hyperfine structure measurement, I could not understand if the goal of current efforts is 5 or 10 hertz, but also a modest 2 or 3 factor of improvement will be needed. It would be much harder because you have to resolve the line shape much more than you have to do it in muonium. But at least it seems from the latest paper, right, the museum collaboration about Rabi oscillation spectroscopy. So we will hear about it in 2 days, but you shoot the muons in and you can really see them Rabi oscillate, because when the muon decays, it tells you where the beta particles tells you where its spin was. So you can see Rabi oscillations live. And this is claimed to be very helpful for reducing the systematic uncertainty, meaning that basically much more statistics would be needed. Speaking about statistics, at least for 1s2s, what we really would need is much more low energy muons, which are maybe the most precious. So a straightforward improvement was just published a week ago. It's an improvement to the only low energy muon beamlight in the world. It's changing magnets. I know it's not easy, but it seems straightforward in a few years. And that would be a factor 2 or 3 more muons. So that's the first improvement. The second is the high intensity muon beam upgrade to the PSI accelerator, and that would give around 50 times more available muons for most of the PSI experiments. This, of course, we have to wait to see if it's approved or not. And last, for low energy muons, there is a new but very successful, so they've been showing each part is working slowly over the last few years, is the new method to moderate muons, which is where we lose most of the low energy muons. And this is called MuPool, and it's a collaboration at PSI, which are working on getting more low energy muons. So taking all of these into account, even assuming that something doesn't work, I think we will have consistently and in time much more low energy muons, and we can think about improvement to statistics. For the hyperfine structure for radio oscillation spectroscopy, you need a pulse beam, and currently we're thinking whether that could be done with a PSI chop beam in a competitive manner to improve the hyperfine. But the hyperfine would be the hard part. So combining everything, we believe on the order of 10 years that the theory and experiment and fundamental constants do not enter here, that one could get a mu from only from Muonium spectroscopy and QED and hydrogen spectroscopy for Rydberg, but it's a small effect, to sub ppb accuracy, and the graph would look something like that, sub ppm accuracy. And considering how much effort and how much new physics scenarios are being taken into account today from the Muon G-2 paper, I would say this is an effort worth going for. And yeah, I think I'll finish with that. Thanks.
Thank you very much. Christoph has some comments.
Yeah. Because this recoil correction have been already calculated years ago. Andrzej Czarnecki was not aware about this work. I have done the calculation 15 years ago.
Okay. You mean the second order recoil?
Yes, it means to all orders. I calculated for arbitrary masses.
Okay.
But haven't presented. But I got this hard part numerically, so it is not accurate enough. But the low energy part is calculated analytically, but using different regularization, because the paper of Czarnecki was after this. So I use a different regularization. Therefore, it has to be redone in consistent manner. But I mean, it is doable, and this is a relatively simple problem.
Okay. Okay.
So these recoil corrections are, I would say, the easiest part of this.
Maybe I'll ask you, can you comment on this one?
Which one? Once again.
The radiative recoil correction. So this is the main contribution also to the Rydberg uncertainty now.
The radiative recoil. So the first order is known. The second. This is the first order is known analytically. Okay.
So you take 10 times this squares when for the uncertainty.
You're talking about the high order recoil, which was addition Z alpha. What is your question?
So is anyone working on reducing the uncertainty in
but
this
please tell me
correction?
where the uncertainty comes from.
The uncertainty comes from uncalculated high order in Z alpha terms.
I see. Then since you express your willingness to get this, we will think about this, okay? It's
okay.
not.
I mean, for us, it will take a long time doing everything else, but I think it's important for the Rydberg constants and the
this is exactly the reason for this conference, that you show what you need, and then we will consider it.
Okay.
Very good.
Thanks. That was easier than I thought it would be.
Andor.
Yeah, thanks. Nice talk and wonderful project. I have just a comment to say. The hyperfine structure in hydrogen should also be improved in view of our upcoming measurement of the muonic hydrogen hyperfine splitting, because then if we improve the 2-photon effects in the hyperfine splitting by at least an order of magnitude, then the QED test will be limited by uncalculated QED terms.
Mhm.